Yes, sir. I think participants are coming, sir. Shall we start the session, sir?
Okay, actually, I'm ready. I mean, whenever uh, everything is ready from your side, we can start the presentation.
Yes, sir. We can start the session now, sir.
Okay, so let me share my screen.
Yes, sir. Sure. Sir,
Okay.
before that, there will be introduction for you.
Okay,
Participant must know about your profile.
sure.
Shall I? Okay.
So, you, you want me to give my introduction myself?
Sir, no, sir. I'll introduce you, sir.
Okay, very nice.
Sparkling gems adorn the sky, and you wish to be like them. A dazzling splendor to beautify, and a long road to excel. A happy morning, everyone. Additive manufacturing is an area where a number of scientist fields meet, and this fact already is a source of attraction for the involved scientists, the engineers, the users, and the public. I am Harishri.
On behalf of on behalf of the Department of Mechatronics Engineering, with great pleasure and immense exultation, we extend a hearty welcome to all dignitaries, guests, delegates for the FTP on additive manufacturing for environmental sustainability. I am Divya.
I am Akshay, and we are here to carry out the session.
Now, I take immense pleasure in welcoming Dr. Pankaj Kumar, Assistant Professor in the Department of Mechanical Engineering at the University of New Mexico. He completed his PhD in Metallurgical Engineering from the University of Utah. Dr. Kumar's research focuses on the experimental and computational approach to elucidate the processing, microstructure, mechanical property relationship in lightweight and high-strength titanium and aluminum alloys and high-temperature based metallic systems. His research focuses on applying the fundamental knowledge of metallurgical and material science and engineering to address the various challenges in additive manufacturing. His productive research career has produced over 40 peer-reviewed journal publications. He is currently serving as a reviewer on over 25 journals and guest editor of journals. He has participated in many national and international conferences in roles such as presenter, conference paper reviewer, technical committee member, and session chairman. We welcome you, sir.
Thank you very much, Divya, for the introduction. Let me share my presentation now. I'm just trying to familiar myself with this platform. One window, okay. So please let me know if you see my screen.
Yes, sir.
Okay, very good. So, very good evening, everyone. And it's early morning there in India. So, myself, Pankaj Kumar, as Vidya talked about myself. So, I'll give you a little bit background about me, as we go for this presentation. So, today I'll be talking about additive manufacturing, essentially what the process is, and what different properties that we see when we use additive manufacturing and what are different challenges that we'll talk about. Okay, so first of all, I'd just like to introduce about my lab at University of New Mexico, what we actually do here in the university. So my lab, where I'm the principal investigator, where we mostly work with the manufacturing research, and we also do a lot of materials research as well. So these are actually basic research portfolio that we have in the group. Okay, so before delaying more, we can start the topic. So today in today's talk, we'll talk about the additive manufacturing. So I'll just introduce this process, what it is, what's all about, what is the global impact of that. And with the example of, fusion-based technique, like one of them is laser-based technique, we'll give an example of the properties and how those properties we can we can manipulate and what are different challenges. So there are two different examples that just taking two different examples. One is fusion based and one is solid state based technique. We'll try to figure out what different challenges we will have, right, when we use the additive manufacturing technique. Okay, so I'm very sure that all of you know what the additive manufacturing technique is, right? It is very different from the conventional technique that we have right now, the rod manufacturing technique, which is a kind of subtractive technique. So those who don't know in details, it's just basically a very simple idea. Okay, subtractive techniques, you simply just machine out the excess material, right? That is what the subtractive means. In additive manufacturing means you just simply add the layers. So essentially, instead of machining out the desired shapes, you actually create the shape that you need without wasting the materials. So that is the one of the advantage of additive manufacturing technique, right? Where you don't lose the material when you process it. Okay. So what is additive manufacturing technique is, right? So this is another example why so important in recent manufacturing area is, yes. Okay, so we'll
Slide
just
number.
carry on. Okay, so we understand, right? Additive manufacturing is just layer by layer technique. So you don't actually machine out anything, right? If you have to make this cup, for example, right, you have to just weld different parts to get the desired shapes. Like this cup is not easy to machine out, right? So what you do is simply you just weld it, different component, just weld it to get your desired component. But additive manufacturing technique overcome that limitations of rod manufacturing, right? You can just layer by layer, you can just make entire thing. Okay. So in general, irrespective of what the process is, additive manufacturing uses 6 different path, right? You just design on a computer and using some interface, using certain, okay. So
Excuse
using
me.
certain, I'm sorry.
Slide is not moving, sir. It is the first
Oh,
slide.
it's not moving.
Yes, sir. It's not changing.
Okay. Do you see any change? Okay, let me try.
No, sir. It is in the first
Okay.
one. First.
Okay. I'm sorry about that. Okay. So let me reshare this slide again. Okay. Let me see if I can do it. Stop sharing.
Yes, sir. Yes, sir. Now only it's coming. Now we cannot see the screen, sir.
Okay, you cannot see the screen. Okay, I'm sorry about this. Uh, okay, so do you see the screen now?
No, sir.
Okay,
Now it's
now,
coming, sir. Now it's coming.
okay. So, excuse me. So do you see change in the slides? No change in the slides? Do you see any change? I mean, the slides are moving.
Yes, sir. Yes, sir. Yes, sir.
It's moving now, right? It's the slides are changing. Okay. Okay, so I was talking about this. I'm sorry about the previous share. So you can see this slide now, right? It's a image of a cup and with different geometries that I'm talking about, right? So it's visible now. You see my slides? Okay.
Visible, sir.
Okay. I just
Can
want
you
to make
change
sure
the
that
next?
it now it changed. Did it change? Did it change?
No, sir. No, sir. It is
Okay,
in the
so let's
same
do.
slide.
Okay, so let me do this. I'll just present just like this. This is okay. Okay, I'll just present like in the editing mode. This should be okay, right?
Okay, sir.
Okay, I think my presentation uh, mode is not working somehow. Okay, so let me just talk a little bit about this. So additive manufacturing we talked about, right? It's basically okay. So if you want, I can just go one by one more time. That should be fine with me. So idea is in subtractive technique, that is the best technique we have. Route manufacturing is an example of this technique, right? Where you actually machine out the desired shape, right? In additive manufacturing, what you do is essentially you just stack the different layers and you just join those layers, right? So that is the additive manufacturing thing. What is the advantage of that? If we extract different layers, right, essentially you don't have to worry about the different complex features. Like internal features is very hard to machine out, right? So you typically join them, right? When you machine out, you typically join them. But in additive manufacturing technique, what you do is you just simply add the layers, so you don't have to worry about the machining. So that is the beauty of additive manufacturing technique is, and that is the biggest advantage of it, right? Okay, so what we do in additive manufacturing, what the process is essentially, right? So it's very simple process. Many of us have done it, right? What you do is you design that what you need, right? Depending on what the application is, you design that on a computer. You don't have to directly go to the machine shop, right? And using some interface, user interface, you feed this to your program, right? Once you feed the program into your computer system, this computer system will be attached to your equipment, additive manufacturing equipment. And after that, you just simply sit and relax and wait, right? Once you printed the part, right? Once my part is printed, you just simply do analysis of those parts. And if the parts is okay, you can use that. So it's very simple process. Designing, we ace the designing part of additive manufacturing process. So we can design anything, right? So we have very advanced software nowadays that we can use to design different parts, very complex shapes. Okay, so where we stuck in additive manufacturing technique, right? We have aced the design part, we have aced the user interface part, we have aced the manufacturing part. So where we are right now, where we are stuck, right? So that's what we're gonna talk about. Okay. So this is the flow diagram of additive manufacturing processes, right? Everything is controlled by computers, so it's not human interference is there. You simply use the computer input to change different parameters, right, to print your part, right? So you need to optimize values to control those. Okay, and these are the user interface that you have, and you can use this user interface through internet. You don't have to really go into the lab. Okay, so that is the beauty of additive manufacturing technique. Is more optimized process. It's just one step process. Okay, so that's the advantage of this process. Okay, so what the additive manufacturing process is, right? So you have a process where you need a raw material, and that raw material you can use to get your part done, right? So your raw material can be your powder materials, liquid materials, and solid materials, right? And depending on what sort of raw material you have, what is the input you have large different types of additive manufacturing technique. You can use the laser technique, laser sintering technique, right? You have the printing process. So either you can use the sintering process, you can use the printing process, right? When you have the liquid metal, you have the extrusion process, and so many different kinds of additive manufacturing process are, right? So, so what are the difference between those processes, right? Which one to select to manufacture different components? That is another question that we need to answer. Okay, so for the same material, can we use all of them, or can we use just the selected one? So that's the idea. You need to really choose the correct process, and that is very, very, very important, right? That's what the process modeling is all about. Okay, so depending on so many things, you have large set of additive manufacturing processes available. Okay, what are the difference between them? So how you create the layer, right? How you bond them, those layers, and how fast the technique can be. It can be supersonic, it can be subsonic, it can be very slow, right? Depending on type of additive manufacturing process you have, you can have the limit of the speed. What can be the resolution? And the resolution is defined by your thickness of the layer, right? Very finer the thickness, higher the resolution of your parts, right? What is the range of the material? What different range of what different materials you can manufacture, right? You cannot use, right? You cannot use the fusion deposition modeling for the metals. So you need to choose accurately which one is better. You need to really talk about the accuracy, right? What is the resolution you need to, right? How accurate or how dimensional tolerance you have. And based on that, you have to choose the correct AM technique, right? So cost is another issue that we always take. We really need to take care about this, right? So cost has been the driver, right? Driver for the manufacturing processes. Okay. So among them, you have so many additive manufacturing processes available, right? How to choose them? So that is another aspect that we really need to understand. Okay. So this is where it leads to. So AM process selections. Okay. So additive manufacturing is very new technique, right? It's not very old. Just like any other technique, is decade old or maybe 2 decades old. So it's not very old technique. So we don't know a lot of things about it. Okay, we expect that it will grow further. That's what is all we expect, right? So right now, what you have is 350 types of additive manufacturing machines available, right? You can imagine that how many variables you can have, and we already have 450 materials that has been printing by different additive manufacturing machines, right? All these have the variables, right? What basic AM process are, we already talked about this, is extrusion, polymerization, powder, right? And material jetting and so on. Okay. Among so many variables, you need to choose one. And why is it so important? Why it matters a lot, right? Selecting one optimal one is critical, right? It's very, very important. Why is important? First of all, it will decide the cost. If you don't choose the optimal AM process, your cost, it will affect your cost, right? You may not get the correct tolerance, you may not get the correct properties of your component that you made out of the process. So you really need to think about so many variables, right? So you need to really worry about uh, what different parameters from each AM process impact the performance, right? So this is very important. So process modeling, AM process modeling is very new subject that we really need to understand. It's not very old technique. Okay. So different what is the different parameters that we really take care about, right? So what the first thing we worry about is product requirement, right? So from there you have to form it, if it fits, if it work, right? That's the idea. And all these are affected by the process selection. Okay, what different process you will choose, what different material you will have, accordingly it will change the type of process, right? So overall, if you ace the process modeling and if you choose the correct process, additive manufacturing technique, the correct equipment, the overall benefit is tremendous, right? You will get the better product, you will get best properties, right? And same time, you increase safety for the humans. So that is most important thing. So you understand why the process selection is important, okay? Right? Okay. So this is all about the additive manufacturing processes itself. So you have the process that we need to select. So out of 450, this is very recent data, right? It's last year data that we have 450 types of AM equipment available. Okay. So let's move on and let's try to look at one of the additive manufacturing process. This is the most common additive manufacturing process for manufacturing metal alloys, right? Laser powder bed fusion technique, where your raw material is powder, right? So essentially, this is the process, a schematic of the process. What you have is this is the component that you want to make. This is the, you see, and this piston is keeps go it goes right down. When you apply a powder, a layer, it goes down by a layer. Okay. So essentially, when you have this powder layer, you just shine with the laser, and the laser intensity is so high that it melts the metal particles, right? And wherever you need to melt and join together, where you shine the laser. That's the basic idea. I'm very sure that you all know about it. So it's not a very different process. The idea is that laser additive manufacturing technique is the most commonly used additive manufacturing process. So this is one short video from YouTube. It's basically it shows you the real-time manufacturing. Okay, so we'll skip this. We'll skip this. Just this gives you an idea of the process. Okay. Okay. So what is the impact of additive manufacturing processes? Right, whatever additive manufacturing advantage we have seen, right? On demand, on site manufacturing, time to market advantage, where you reduce significantly the time. You don't have to worry about transportation of these cars. You can make high complex design at the present a specific design, right? All of them actually adds to the economic and environmental incentives, right? So many advantages we have. You must have studied about this, right? All of them actually goes to the reduced material waste and the energy. It's all about saving the energy. So you want to make manufacturing efficient, you really want to reduce the energy or make energy efficient techniques. So additive manufacturing advantages we have that adds to the saving the energy. So that is the biggest advantage of additive manufacturing techniques. So both of this gives you the environmental effect and the economic effect. Okay. Okay, so many advantages we have. Why we are lacking to implement those technique, right? We already have is the design part. We still need to work on the AM process modeling, right? AM process modeling, you need some sort of input, right? You need certain input to choose the correct parameters, and we don't have those input available. So we don't have enough input that we can select the correct parameters. So that is another disadvantage of the process. It's not the process disadvantage, is essentially your process, the history. Basically, it's very new process, so we don't have a lot of information available. Okay, so different challenges we talked about: insufficient knowledge, right, of these processes. We don't know what the performance will be. It's very, it's a problem. It's not a problem, in fact, it's just a limitation. Okay. So reliability is another issue, and that we will talk in details in the next few slides. Why reliability is so difficult in additive manufacturing processes, and then limitations on materials use. So there are certain materials that you can use, right? Certain materials that you can use using additive manufacturing technique. Okay, so far we have made a small build volumes, right? In fact, we already have the jet engines made out of additive manufacturing technique is used in NASA, but those are not functional. They just developed it. Okay, those are not functional. So far, the functional parts are the volumes for the functional parts are small. It's not very big. Okay, so because of all these limitations, additive manufacturing is contributing less than 1% in total manufacturing market. So that is a huge gap, right? So we have advantage here. In fact, if you add so many, if you add your uh, studies, it will add to your manufacturing. It will contribute to your manufacturing input. Okay. Okay. So success of additive manufacturing technique, right? What we need, right? When we talk about the powder-based additive manufacturing technique, where raw materials are powder, right? That is the one that I'm using as an example to know the limitations, because you have 450 types of additive manufacturing process, right? So we cannot talk about all, but this is one of the example that we want to take, understand, and try to see what different challenges we can have. Okay, so additive manufacturing technique based on powders, you need to have the powder processing information. You need to know what the processing condition changes your performance of your material, right? To do that, you really need to understand the materials when you make it, and then you want to try to understand the properties, how from the powder processing, how it actually changes the performance. So overall, you need to get all this thing connected, right? So focus on combining the different research aspect to contribute for the success of additive manufacturing technique. So additive manufacturing is not one person job. It's like looks like it's like entire community, engineering community needs to tackle the challenges. Okay. Okay, so where reliability comes from? If you talk about powder-based technique, right? Powder-based technique, the reliability is an issue, and that issue is not new. That issue has been for very long time. Okay, so whenever you use powder-based technique, this is the thing you will see. So this is an example for the titanium alloy, titanium 6 aluminum 4 vanadium alloys. And if you look at this diagram, percentage elongation relative density, right? In additive manufacturing technique or any powder based component, what you want is the best density you can have, the highest density you want, like very close to the density. You always have residual porosity, right? But you want to be very close to the theoretical density. But what is the challenges here? What you see here, when you go from 94% relative density, if you go to 100% density, the problem is the reliability here, right? These are manufactured not by additive manufacturing technique, but these are made by powder metallurgy technique. But powder metallurgy technique will have the same issue as additive manufacturing technique is. Okay, so you can see you have large variation in elongation for the same material with the same microstructure. So your ductility or the elongation can vary somewhere from 7% to 20%. So if you make one material, you are not sure what will be your ductility is, right? So this depends on right. This variation comes from the defect, and defects are all the powder based technique. The defects are coming from a statistical nature, right? You cannot control it. It just simply comes. It's very hard to control them, right? So this is one of the studies that we have seen that it the fracture variation, very significant variation. So the overall conclusion we can draw from here, right? Densification, the components from powder always lead to unpredictability, and this is a statistical fact. process. We cannot control it by process itself. Okay, so this is biggest challenge we have at this point. Can we change that? Or can we control it? Yes, we can, but not during the additive manufacturing process, but after that, right? So you can in fact control the performance by doing the post-processing fact, right? You can just control the powder process parameters, and you should be able to get the properties you need. For example, here you see you have different powders, and different process, you have different properties altogether, right? You see the stress strain curve, different powders, different process, you see you are able to achieve the properties to the very close to the state of the art mill annealed conditions. So you see this table, it clearly shows that behavior. So if you control the process by doing post processing method, you should be able to get the properties that you desire. Similar to the fatigue curve, if you look at the mill annealed condition, the rod samples, and if you look at different particle size and the process, the black one, you see the black dot, it actually able to shows the property close to rod product. So this is encouraging observations, right? In additive manufacturing process, you can do the similar idea. That's why the post processing becomes very important. So additive manufacturing process itself doesn't give you the quality that you need, right? You always need to post process your material, right? Okay, so this is how it looks. If you look at the microstructure of those powders starting from -325 mesh, which is the coarser particles, this is finer particles, right? You see the significant difference in the defect. The black dot you see are pores. Okay, as soon as you apply the post-processing isostatic forging technique, all these defects has been completely eliminated, and the microstructure looks like your rod product. So manipulating the dominating factor, right, you can improve the properties of your material. So all this technique actually eventually impact your properties. That's why you need to select the additive manufacturing process, and if you need the post processing to change or manipulate the defect. Okay, so these are just an example where why it's so important, right? Okay, so let's talk about, we understand the powder process. Powder process actually changes significantly. It actually significantly changes the performance of material. Okay, so fusion based technique, we already talked about the powder weight, and we talked about and then there is another technique, directed energy deposition technique, right, where we have everything here. Okay, both starts with the powder, and the idea is very similar, right? Only the process itself is little different. Okay, so let's talk about the processing condition, how the laser parameters changes the performance. Okay, so you have different parameters that you can control. You can control the laser beam diameter, you can control the hatch distance, you can control the layer thickness. So all these are parameters that you can control, right? And if you control that, you can control the laser power density. So that becomes very important, right? So this is an example how the process parameters for the laser changes the quality of your product, right? So if you change the speed, right, you make very bad samples. If you increase the power, even though you make very good samples, but you increase the cost. So you really want to optimize the condition where you want to minimize the cost, but you want to get the best materials, right? So this is the way to go. Okay, so this is how it affects, right? How does the laser parameters changes? That's how it works, right? So let's look at the example of the porosity, and how it changes with energy. Okay, so you can see the porosity and energy relations. And if you look at slight increase in energy significantly decrease the porosity level in the samples. So that is very important. That is very important observation, right? So the drastic decrease in the porosity with the energy. So this is important, right? And the porosity also changes linearly. So there is a difference. The porosity depends linearly on your scan speed, and porosity depends, right? Porosity depends non-linearly on energy. Okay, so based on all this observation, you can see that you can have the same amount of porosity with different energy levels, right? Less than 1%, you can have 10.3, 7.3, 8.9 joule per millimeter square energy density you can have. But what the best we can optimize it. So even though you can optimize with 4.7, so this is the lowest amount of energy need to get less than 1% porosity. So this is all the optimization, and it depends on very specific to the equipment, to the materials. So you need to optimize your machine, you need to optimize the materials, everything for different materials. So it's very cumbersome job. It's not easy. You have to do a lot of experiments to optimize one process. Okay, so these are the different challenges that we have. Okay, so what different challenges we talked about? Unpredictable mechanical properties. That challenge is still there, right? We have to really take care about the process itself to really make predictable properties. Okay, large artificial grain microstructure is another issues. If you look at the microstructure, the grains are really large. So I'm not sure how much you are familiar with the microstructure. So microstructure actually changes the properties drastically, right? You want very spherical kind of microstructure, right? You want a spherical grains in the microstructure, but in additive manufacturing process, you have elongated grains, and because of the elongated grains, you have the texture in the material, right? Your properties are directional dependent. So it's very hard to keep track of the directions. So when you use any materials, you don't really think about the directions before using it, right? You just simply use it. But in additive manufacturing technique, because of the grain structure, you have the properties that are different in one direction, properties are different in other direction. So that are different challenges that we really need to talk about. So high surface roughness is another issue that we need to take care, right? So surface roughness, whenever you want very finished surface, right? That gives you best properties. But in AM product, you don't have that. But again, the surface roughness changes with the process parameters. And you see, this is an example for the stainless steel material. And you see, with increase in space, or depending on what the parameter is, your surface roughness can vary, right? For example, scan speed changes your surface roughness. You increase the scan speed, your surface roughness will increase depending on what is the laser power. So all these parameters actually changes your performance on the surface, right? So this is important. So these are challenges we really need to take care of. So the post-process technique that we have developed recently, right? And we, in fact, we cannot use during additive manufacturing process. You really need to do the post-processing. That's why you have the hybrid manufacturing technique, okay? Where you simultaneously make and simultaneously remove some materials, right? You can also do the post-processing method to remove the surface roughness. And using different technique, you can have, the surface roughness reduced from about 10 micron to less than a micron. So that is very significant improvement in the surface roughness, okay? And these are different, with the different parameters, and we are able to get very surface roughness, very finished surface roughness. About mean surface roughness, we got about 2.2 microns. So surface roughness, the mean surface roughness reduced from 10, which was initial, surface to 2.2 microns. So that is significant difference, right? Okay, so those are different challenges with the fusion technique. You have the microstructure challenges, you have the surface roughness challenges, right? You have the processing challenges. To overcome that, people just exploring different ideas, and then they come up with an idea of solid state manufacturing technique, right? Where you don't melt the particles. You actually start with the powders and you don't melt them, right? So this is cold spray based technique. People also calls it sometimes supersonic deposition technique. So essentially you just accelerate the particles at very high speed, and it just deforms at the interface and forms a layer, and you just keep continuing the layer to make your 3D component, right? So different controlling parameter you have is particle size, processing temperature, and the gas pressure that you can control. But what is the advantage of this process, right? What is the advantage? Why people are looking at it, right? So low temperature processing, no solidification defect like a fusion based technique. There is no contamination. I mean, you have contamination, limited contaminations. Okay. Most important is the powder characteristic doesn't change because it didn't melt. So you start with the AQX grain structure. You may have the AQX grain structure in the particles. The density is very high. The grain structure is very good, right? And if you compare the microstructure, this is the major limiting factor of fusion-based technique. You see the grains are different. So if you look at these grains are more of spherical, right? AQX grains. If you look at this grain, it's more like lines, like columns, right? So the properties will be very different, right? But what are the different challenges here? What is the different challenges here? We have everything here, right? We got a very good microstructure. That's what we needed, right? So look at this, right? Look at this. So this is the tantalum material. So tantalum material is very high melting materials, right? So if you want to additive manufacturing using fusion technique, you need to use large amount of energy, large laser power, right? In cold spray technique, at 800 degrees centigrade, you are able to manufacture the material. Okay, so you don't need to go to really high temperature. In fact, you got your high dense components at 800 degrees centigrade. So this is amazing, right? You don't have to really spend so much of energy, so it doesn't cost a lot, right? What is the problem here is, you see the surface. This is the top surface of the cold sprayed materials, right? Excuse me. Excuse me. So these are the tantalum particles, and you see the interface, right? So tantalum particles, depending on what is the particle size, you have the surface roughness. Okay, so you have the surface roughness. So you can control the surface roughness. You can is a challenge, and you don't want to use the rough component in your applications, right? You always want to have very finished, very fine surface. So this is the challenge that we really need to worry about, right? Post process is one way that we can do it, and then you have a hybrid technique that you can simultaneously remove materials off. Again, you are losing materials. What is the advantage here? You see the grain sizes, it's very small. You are talking about less than 2 microns. So it's very a small grain, average grain size. There are some grains that are really big, but most of the grains are less than 1 micron. They are in some micron, right? So this is important, right? At the interface, if you look at, these are the interface. So interface, you have the very fine grains, right? Those grains actually tells you that their interface is metallurgical bonded. So they are very strong. The layer itself is very strong. You cannot just simply break it. Okay, just like complete metallic structure. And this is, when you heat treat it, your average grain size changes. Of course, you expect grain size to change. Okay. So the idea is you can optimize the grain structure, but your surface roughness is another issue that we really need to worry about. Okay. Okay. So what are the challenges with the cold spray processes? Right. You have, of course, the defects, right? The porosity you see, right? You have the micropores, and this is example of titanium. This is an example of titanium. Okay. So titanium is actually deposited on this layer, magnesium alloys. Okay. So you can have the micro pores and you can have the cracks. So crack is always a problem because you are spending so much of strain energy, right? And because of that strain energy, you see the crack. So cold spray sample, if you look at it, it's a brittle sample. Even though your material is ductile, right, by nature, after the process of cold spray, it becomes brittle. It's really brittle. It's just like glass. If you drop it, it just simply fractures, just fractures. But in situ, if you look at it, you see the cracks. These cracks happen just because of the residual stress. So much of energy, strain energy that you are doing it in the process, it cracks, right? Some interface doesn't join together. It's a statistical process itself, right? So these are the challenges that we really need to work about. So these are tantalum. You look at it, these are the cracks that you see, right? And these are the surface roughness that we have to worry about. So how to control those? How to control the crack? So only way we have is post process it. Just do it one more time with something else, and this is what we have. So we tried closing the defects. If you look at the defects, right, we use friction stir processing, and what we saw is the defect at one side is significant. It's more than the defect is more than 10%. But if you look at the friction process interface, the material is very, very clean, and the properties changes significantly. So your hardness changed from 3 to 5 gigapascal. So that is significant change in the properties. But you really need to take care about the defects, right? So addition of mechanical working with cold spray changes the properties. Okay. So overall, in summary, implementation of AM right now is a challenge, and we have seen what different challenges we have. To implement AM, what we need to do is you need to do the powder analysis and qualify those powder for additive manufacturing technique, right? You need to take care about the surface finish and the texture that we saw. AM flaws that we need to understand and how to tackle those AM flaws like defects, like cracks, those and the grains. Eventually, overall, including all this, you need to really define or establish the guidelines for manufacturing, right? And you have to tell what is the manufacturing limit for each manufacturing technique. So you really need to fill the research gaps in various degree of research need to establish the AM technique, right? So this is all about the additive manufacturing process and challenges. I'll be happy to answer any of the question you may have, right? Thank you very much. So I think I'm on time. Uh, so we have. So I'm on time, right? It's 10 o'clock. Is
Participant, you can ask any clarifications or queries.
right. So we got few minutes to, I can always answer you whenever you feel like, you can reach out to me. Or if you have any question right now, I'll be happy to answer now.
Good morning, sir.
Yes.
Can I ask some questions?
Yes, sure.
Sir, how support structures are rectified, sir?
I'm sorry. Can you ask one more time?
Sir, how support structures are rectified? Sir?
How surface structure? You ask how the surface structure can be modified, is it?
Yes, sir, in FDM process, how support structures are rectified?
Actually, it's very hard to hear. But if you're asking about the surface structure in additive manufacturing process,
Sir, I'm Veerapan, sir. I think he asked about the fuse
Mhm.
deposition modeling process. The participant, I think,
Okay,
Mr.
okay,
Arun Murugan is asking. I think he is asking about fuse deposition modeling, FDM process. Suppose structure, wax suppose
okay,
structure is asking. I think, sir.
okay. So you're asking how FDM process can be changed? Actually, I couldn't
Yes, sir.
understand the question. I'm sorry about that.
Okay, sir.
Actually, your voice is cutting down in between.
Sorry,
So,
sir.
so I
Yes, Mr.
think if you can.
Arun, kindly don't unmute. Sir is trying to convey some information. Kindly don't unmute.
Okay.
Sir, okay, sir.
Okay, I think if you have things, you can always email me. I think it's easier, and I can, you can always email me. So fuse
Okay.
modeling deposition. That's what you're asking. I
Yes,
think
sir.
there is some internet issue. I think.
Maybe in my side.
Yeah, I think if you email me, that way it is much better, so that I understand the problem or the questions correctly.
Yes, sir.
Okay. So thank you everyone, and reach out to me if you have any questions about things, then we can talk on emails. Okay. So thank you everyone, and it was nice
Sir, I have
being.
clarification, sir. Myself, Veerapan.
Okay. Yes.
Sir, may I ask, sir?
Yes, please go ahead.
Sir, you have shown the surface texturing microstructure, what you have done using the cold spray method.
Yes.
You have seen the, yes, sir. And yes, here also I have some doubt regarding this microstructure.
Okay.
How we can explain this? How we can understood by this grain structure, sir? What's the difference between powder bed fusion and
Okay.
this cold spray parameter, sir? You have shown the
Okay.
three microstructure which is protruding some when you compare the surface roughness, I think that
Right.
microstructure.
Yes. So if you look at, this is the cross section image. So these are,
Yes, sir.
it is on the top without polishing, right? This is how the surface looks like. When you cut the
Actually,
sample,
tantalum is sprayed on some substrate, sir.
yes, the tantalum is sprayed on a steel substrate.
Okay, steel
So there
substrate,
is
sir.
a
Well, sir.
steel
Well, sir.
substrate, right? You just simply cross section it. On the surface, you see so much of rough surface, right? And when you cross section it and look at the microstructure at the cross section, this is how it looks like. So your materials, if you look at here, if you look at these ones, right, these are
Hmm.
the interfaces from the top, for example, they are metallurgical bonded, right?
Yes,
So
sir.
when they are metallurgical bonded, at the interface, you have very high strain energy, right? So at the highest strain energy at the interface, these are particles. If you look at this, the bigger grains are actually the particles, right? So those particles are in contact with the different particles, but because of the strain, they join together, right? So at
Yes,
the
sir. Yes, sir.
interface, because of this strain energy, you recrystallize the finer grains. So those finer grains actually hold the two particles together. That makes sense?
But how far is the bonding strength, sir? When we spray in the cold, actually it is done in, I think, 300 to 400 degrees centigrade.
No, 800 degrees centigrade.
Okay, 800 degrees.
Right.
But how it is named cold spray? That's a confusion for me.
So, no, cold spray is basically you are not using temperature. You are using the strain energy. So how you get the strain energy, you are just impacting at very, very high speed. And if you look at the speed is 525 meter per second, it's like a bullet.
Okay.
It goes really and just impact. So when it
That's
impacts,
why you use that sonic nozzle.
yes, that's what you use the sonic laser. So when you
Okay.
have the impact, your spherical particle becomes kind of plate, micro plates,
Okay, sir.
right?
Okay.
So you can micro plates you have. So all these are micro plates, I would, if you want to think about
Now I
that, right?
understood. Now I understood. The
Okay.
microstructure is something like a form of platelets.
Yeah, it's kind of layer. If you look at
Layer.
this,
Okay.
it's one layer, second layer, third layer, fourth layer, five layer. And in between the layer, you have very fine micro grains. So that grain says these are micro structurally intact. So bonding is metallurgical bonding, right? Okay, makes
Okay, sir.
sense.
Thank you. But
Thank you.
uh, according to your one practical experience, what will be the significant process parameters in powder bed fusion, sir?
So the significant process parameter is very hard to actually, say about it. It depends on the material type. So if you talk about aluminum, right? If you talk about aluminum, your reflectivity becomes very significant thing, right? But
Reflective?
aluminum reflects your laser energy, right? So
Yes.
you need a
Yes.
lot of energy to actually melt your aluminum. What you
Oh,
think that aluminum can melt at lower energy
yes.
level, right? But
Yes.
it's just reverse. In fact, it's easier to melt inconel than melting aluminum. So it's very hard to say which parameter is dominating. But if you have to say in global
Mm.
picture,
Mm.
in a global picture, and it all depends, right? What you want. So
Yes,
that's
sir.
what
It
the
depends
process.
on the material. Right.
It depends on the material. It depends on what you want. You want more pores, less pores. So it's very hard to actually tell which one is more dominating factor, right? So if you have to make very dense product, you want to have very good hatch distance. You want to have optimized laser parameters. So
Okay,
it's
sir.
very hard to comment on that,
Okay, sir.
So
Thank you a lot
it's
for giving clarification and wonderful insight information about this powder bed fusion.
very good.
I think this is a new for me, cold bed fusion. And also you
Right.
have pointed out some more number of additive manufacturing materials you have shown in the
Right.
slides. It's
Yes.
quite
Yeah,
interesting
I
for
think.
us.
Thank you very much. I think, yeah, we have a lot of things in additive manufacturing. You have 156 parameters that plays role. It's not just five
156
parameters.
lots, sir.
A lot of parameters are there. It's just five parameters we talked about, but there are like 156 parameters that we really need to control. So
Okay.
those are challenging to talk about, But
But
it is very.
in this
Mhm.
slide, you have shown that 1% of the, I think you have shown since a very,
Yeah,
you are using very, up to
1%.
least.
Yes.
Mm.
So density, you are saying?
Not density, sir. Total production or
Yes,
total
total
consumption.
production is less than 1%. Yes, total production is less than 1%. So that is, but it's very new technique. So we expect that probably after 10 years you may have more.
Mm.
The
Yes, yes.
contribution will be more.
This slide, sir. AM contribute less than a tenth of the 1% of total manufacturing.
Right. So this
Thank you,
is.
Lord.
Thank you very much, and thanks for having me here in this uh, the workshop. And just reach out to me with any questions you have.
Thank you, Lord, sir.
Thank you very much.
Thank you, Lord, sir. Thank you, Lord, sir. I will
Thank you.
reach afterwards, sir.
Yes,
Thank you, Lord,
very
for
good.
your accepting invitation. Thank you, Lord, sir.
Thank you very much. I'll talk to you later then. Okay.
Thanks
Good
for your
night, everyone.
informative presentation, sir. It made us curious
Thank you
to
very
know more about it. We would like to inform you that we were very glad to have you today here, sir. Thank you so much, sir.
Thank you very much, and have a very great night. I'll talk to you later, maybe.
Thank you, sir.
Okay.
Thank you.
Good
Thank you.
night.
Thank you.
Good night.
Thank you.
Bye.